another example of what one can do in order to reduce the size of power management system for portable applications. So a typical power management system for portable devices usually looks like this. So we have battery cells, then we have front-end DC to DC converter that creates intermediate bus voltage, and then connected to that intermediate bus voltage, we have a number of point-of-load converters providing well-regulated voltage for different parts. For example, 3.3 for analog electronics, then 1 volt or even lower voltage for digital parts, and then we can have even higher higher voltages for some, for example, for LED light, back panel lighting, and so on. Usually in these topologies, this front-end stage is usually bulky, and all of those downstreams converter operate at the full voltage swing, meaning that the voltage swing at the buck converters here goes beyond between 0 and 5 volts. Now what we can do, we can look at the extension of concept of reduced voltage swing and to design to design a battery converter. One of the things that is also important to mention is that if you look at power management systems today, inductors and big inductors and output capacitors take a significant amount of overall PCB area, and we are going to get to that point soon. So the topology that I would like to show you, or what you could do in order to reduce the size of the inductors in the power management systems, is to look at the differential buck principle. So differential buck principle is the idea that rather than changing the switching node voltage between 0 and full input voltage, that we can switch the voltage between the two values that are very close to the output voltage. For example, if the output voltage is 3 volts, we can just go and a little bit lower than the input voltage. What it then 3 volts, for example, 3.3 and 2.7. If you do it, and if you think in terms of what we are achieving in terms of the voltage swing reduction, we will be reducing the voltages here at the top. So rather than like for conventional buck having this voltage that is switching between VG and -V and -V, we can have two new values, for example, somewhere here and somewhere here. Now, from the analysis, from the review of the reduced voltage swing principle that we looked at the beginning of this lecture, what we can understand is that if this variation is very small, we can have a really huge reduction of the inductor sizing, a huge reduction of the inductor. Now, how this principle is applied for the power management system. So here, in order to achieve these voltages, we know that power management systems usually incorporate multiple outputs. For example, this is high voltage output at 3.3 and 1 volts, and then depending on the output value, we can put as a front end stage something like a capacitive divider, and we will see soon that it is actually a switch capacitor converter. And then rather than switching between 0 and full bus voltage, we can switch between these type of voltages. So differential buck is a buck converter whose is connected to the full input voltage, but at the two taps that are where one is at the voltage that is higher than the output voltage, and at the second tap is at the voltage that is a little bit lower than the input voltage. So now, since we can reduce the voltage swing here, we can have also a few other benefits. Now, if you think about this switch 1 and switch B, they are operating at lower blocking voltages than if what they would be operating at in the case if they had run from the full swing, meaning that due to the lower switching, lower blocking voltage, we can run them at higher switching frequencies and still have the same switching losses, or actually even smaller switching losses, because the switching losses directly depend on the blocking voltage, have a square relation on the blocking voltage. So in this case, as the front end stage, we are using a switch capacitor circuit. So this switch capacitor circuit has two flying capacitors and a capacitive divider, where these two flying capacitors are used to balance the voltages, or to keep the voltages of the capacitive divider of the output at the desired, there is 1/3, 2/3, and a full voltage. And this front end stage operates at a fixed operates at a fixed rate, fixed conversion rate, where the switch cap circuit is the most efficient. And each of these caps here has 1/3 of the voltage, and the same applies for the flying capacitors. Both flying capacitors have 1/3 of the bus voltage. And now the red and blue lines show the switching sequence. Initially, during the first phase, switch capacitors CS1 and CS2 are charged, and then during the second phase, they're transferring their energy to the output caps. And now, as the output stage, what we can connect, we can connect in this case 3 differentially connected buck converters, where the first one will be producing the highest voltage, the second one will be produces the intermediate voltage needed for bus, and the bottom one produces the lowest voltage. And now, if you look at mobile applications, usually we have two cell input, or 2 cells stacked on top of each other, where the voltage changes between the depending on the state of the charge of the cells, between 5.4 and 6.6 volts, but it can go even lower or higher, where here we are assuming that voltage of one cell is about between 2.7 and 3.3 volts, but in practice, the variations can be even bigger. And then the output voltages here on the taps are here we have 2/3 of the voltage. If the input is 6.6, this voltage at this step will be 4.4. The voltage at this step would be 2.2, and then if the voltage is 5.4, here we would be having 1.8, and here we would be having 3.6 volts. What it means is that, for example, if you want to provide 3.3 volts for 5.4 input case, this voltage would be going between 1.8 and 3.6 rather than between 0 and 5. This allows significant reduction of the size of this inductor L2. Similarly, for the top voltage here, the voltage will be going between 3.6 and 5.4 if you want to produce 5 volts at the output. And then the operation of this circuit is controlled by a digital converter. This digital converter performs 2 things. So it implements voltage, it is integrated controller that regulates all the output stages. And then on top of that, it also measures the tap voltages here and implements some kind of feed-forward operation. The reason why feed-forward is needed is because very often in a modern portable applications, this bottom cell, this bottom load is actually the largest load. It is usually related to processing unit and graphical units, meaning that this capacitor gets discharged faster. And now, in order to keep this, in order to keep the voltage regulation, what we can do here, we can measure the voltage at this step and use feed-forward term to recognize those kind of conditions and improve transient performance of the converter. And here we are showing the case for when the battery is fully charged. We can see here that voltage is 2.2, 4.4, and 6.6, and then we're looking at much smaller reduced voltage swings. In this case, the voltage swing for each step is just 2.2 volts compared to 5 volts that we needed for the full voltage swing. So now, if you compare that with the conventional structure, we can look at the normalized values of the inductance value needed and also the switching losses. So the first diagram shows a reduction in the voltage swing compared to the nominal case, compared to the case when the voltage will be going between 0 and 5 volts. So we can see that the voltage swing is reduced to 44% of the original value. This 44% of the original value in the reduction of the swing results, if you calculate for the same inductor current ripple, in just 49% of the inductance value compared to the original case, the inductance that you would need in the original case. And then it also reduces switching losses just to 44% of the nominal value. And here we're showing the switching frequency as nominal frequency, meaning that this multi-stage is run at the same frequency as the original stages. However, since we have huge savings in the switching losses, we can double the switching frequency, or in other words, we can run this converter at a higher switching frequency than what we would be running otherwise, and still be better in terms of the switching losses. So the nominal switching losses in this converter are now 88% if you double the frequency of that, what we will be seeing in the conventional converter, and then the inductor reduces even further. Now it becomes just 25% of the original value compared to what we would be seeing for the conventional buck. Now, what this allows us, it allows us to do full on-chip implementation of the converter. In other words, one of the biggest challenges in power management applications are that these inductors and capacitors take a significant amount of PCB area. And as mentioned at the beginning of the course, these inductors are probably the largest components of the power management systems and among the largest components, overall components in power management ICs. So now, by reducing the requirements for the inductor, you can put everything on a chip. So this area, this diagram shows power stage plus plus switch mode plus switch cap circuit, and then it allows possibility for putting the on-chip integrated inductor. So this on-chip integrated inductor has been developed by Tyndall Institute in Ireland by Professor Kian Omatuna and his group. There is a question, just give me a sec to read the question. Does the lower gate overdrive voltage on the power switches not lead to higher R-on and impact on the power efficiency? Okay. So there is a question regarding the gate voltages for these transistors, right? So basically, now if you think about these transistors actually now can run, it can be rated for much lower voltages than the fully rated than the transistors that need to run at the full swing. Meaning that by the fact that they are transistors rated for the lower voltages and practically the same current, we already have smaller R-on resistance. The gate drive voltage, we can provide any gate drive voltage that these transistors need, and then you can even do more. You can also do some kind of utilization of energy from one gate driver to the other, and so on. Something that has been presented by the Texas Instruments and in the work of Giacomo Calabrese. Okay, so for the demonstration of the entire circuit, on chip, water represented the low currents and switching frequencies. I assume that the bond wires are the inductors. I'll get to this point soon. So what this allows us to do is to put the entire inductor on a chip. So basically, this is the inductor that has been developed, as I mentioned, by Tyndall Institute in Cork, Ireland. But the problem was that the inductance value was, even though this inductor was able to handle a few hundred milliamps of current, or even beyond 1 amp of current, the problem is that the inductance value of this inductor was so small that it was hard to be utilized in conventional topologies. But now, by looking at this switch cap combined multi-level and differential buck topologies, the requirement for inductance value have been reduced such that full on-chip implementation, full on-chip implementation is possible. Or to be more precise, implementation of both on-chip inductor and that silicon power stage and the controller as a multi-chip module. So basically what we have done, we have created a multi-chip module consisting of these on-chip inductors and the power stage and the controller that I have shown before. And this diagram shows integration of the case for two outputs. There are two Tyndall inductors, and under the inductors is the chip that I was describing. This is just the zoomed version of the solution, and I will show some results. So in this case, the front end stage operates at 580 kilohertz, while the buck converter operates at 10 megahertz. Again, the reason why we are able now to operate it at such a high frequency is such a high frequency is a really low voltage swing. In this case, for the two output case, just as demonstrator, we are showing the input voltage of 3 volts and two outputs at 1 and 2.5 volts. And these are the values of the inductor and capacitor. We can see that in this case, we are able to use inductor at just 100 nanohenries, and these are the parameters of the MOS transistors that are implemented. So the first board that is implemented here is with the off-shelf inductors, and then the second implementation here is with the on-chip inductors. I'm not sure if you're able to see it. I will try to zoom in this picture here, and just to show you where the inductors are here. So I'm not sure how much you can see here, but the inductors are here just bounded, seen as like small bumps in the on the in the package. Yes. Hello. Now there is even more you can do this with this, is that you can also integrate the battery balancing feature. So what if you look at this configuration, we know that this intermediate switch voltage, the way this converter operates, must always be at 1/2 of the input voltage. And then if you have two battery cells, by placing an inductor right here in between, we can immediately incorporate a battery balancing feature that will make sure that this intermediate voltage is always kept at half of the value, at half of the input value. And what is really interesting here is that in this case, if you put inductor, you also improve the efficiency of the switch cap stage, because now you always have charging and discharging of the caps through the inductor, meaning that you're avoiding typical problem for switch cap circuits, and I'm going to address it soon, related to non-adiabatic charging and improving efficiency of the front end stage. So this diagram shows test of the shows further test in comparison with the conventional buck. Here we can see here that for conventional buck we have swing of 500 milliamps, 505 volts, here 2.2, and we can see that due to the reduction of this voltage swing, we also have reduction in the inductor ripples. So basically this purple diagram here shows inductor current ripple for the on-chip implementation case. And then, as mentioned before, that we cannot just go with the size reduction with efficiency improvements. And here, this diagram shows efficiency improvements compared to the conventional converter, conventional downstream buck. So differential input buck here that is providing 1 volt has a peak efficiency about 90%, and the similar buck created out of the buck with the same rating and running at the full voltage has lower efficiency. So we can see that by using this reduced volt sink principle, we can also not only reduce the size of the inductor, but also improve efficiency. And that was our ultimate goal at the beginning of this course, or when we started looking at new ways to improve power to reduce both size and improve efficiency. And this diagram shows just efficiency of the front end stage of that switch capacitor converter, that flight loads is really high, and then as the current increases, the efficiency drops, and that's something that is expected for switch cap circuits, because as the load increases, we also have both increase in the conduction and switching losses, or bigger ripple across the capacitors in switch cap circuit.